everybody. This is Open Research Institute's meeting. This is a FPGA meeting that talks about our FPGA or Field Programmable Gate Array projects and digital signal processing projects that we have going on. The format of this meeting is we have a roundtable and we talk about what we've done over the past week and what we have planned for the next week. And if we have any roadblocks that ORI can help with, and if we need any resources. And so I would like to turn it over for a report from Aaron. So go ahead and tell us how it's going and what you need.
Sure. I didn't have a whole lot of time spent on this last week. It was the kids' spring break. But I've been able to get further along on the HDL simulation with the GHDL and the GTK wave and the MSK modulator. I'm able to run through the test. But since there's been a lot of changes to the modulator itself in the last couple weeks and months, so I'm in the process of updating all the inputs and the outputs so that it actually will actually get data through the simulation and plot it out as it's supposed to be. But I did that. I'm still waiting on the parts for the Pico tuner, but they're soon to be. Oh, I'm excited about it. So they're to arrive soon. So I'm going to build that in the next week. Other than that, I don't have any roadblocks, and I'm okay on. I don't need any resources at this time. Thanks, Michelle.
Awesome. Well, thank you so much. Okay, so Paul, why don't you take the floor and tell us about all of the things that have been going on with Opulent Voice?
Okay. This has been a big week for progress, not so much in fixing Opulent Voice implementation, but in characterizing it. We've hit some milestones and done some things that we hadn't done before. So let me run down where we are on that. The test setup that we're using is two Plutos. One of them is transmitting, generating a pseudo-random bit sequence, and both of them are receiving. The second one is independent to some extent, depending on which test scenario we're running. So the first thing we did since last week was modify the application code running in the Pluto that supervises the reception. So instead of letting it run for a very short period of time and then resetting everything, whether it succeeded or not, and then possibly trying a different set of parameters, which is how we'd set it up to search for gains for the PI controller in the loops that lock the frequencies. Instead of doing that, we're running a more of a tracking scenario where if it's successfully receiving, we just let it be, and that can stretch on as long as we like. We can interrupt it whenever we want, but it can run indefinitely. So the first thing we did was just prove that works with our existing setup, which because of the uncertainty introduced by having frequency errors, we had slaved both of the Plutos to an external clock source, the same external clock source with a splitter to start with. And that simplifies things so much that we were able to make good progress right away and are able to actually transmit bits from one side to the other for a long period of time. Having that implemented in the test code, then we're able to start doing some other characterization tests. The first thing we tried to do was a dropout test, where we're able to vary the frequency of the two Plutos separately using external oscillators. And we tried a search pattern, gradually increasing the amount of frequency error between the two as it tracked to see where it would drop out. And the results were good. We got up to about 42 kilohertz of frequency separation before it dropped out. That's one data point really, although it took a while to collect it. But that's consistent with what we were expecting more or less, and maybe a nice number to start with for tracking purposes. This means that once we get acquired and receiving a signal, then frequency errors that crop in from from one source or another uh, are not going to be a problem. We're able to track them out up to about 42 kilohertz. Once you're able to do that, then the next question is, if you do drop out, what does it take to reacquire? Um, so we tried a series of tests, um, relock tests, if you want, where we'd start with it unlocked and hit it with a signal that was off frequency by a certain amount and see if it succeeded. And we started from the dropout point of 42 kilohertz and pulled back in and back in and back in and back in. And we got all the way to zero and it still wasn't receiving. So something was wrong. There was some problem with starting the reacquisition that way by just changing the frequencies. And this is not surprising because there's lots of memory in the demodulator. Its accumulators might have been so wacky that it couldn't find itself. Um, so we tried to eliminate all of those uh, uncertainties by restarting the application code every time, which reinitializes the chip and gets things going. And again, we ran a test search pattern trying to find what frequency it could relock at. And again, we got all the way down to zero and it wouldn't relock. This kind of is surprising. We think we're reinitializing everything, and yet somehow we're not. It's not able to uh, reacquire after having been off in the weeds somewhere somehow. So there's some memory somewhere that we don't really understand. Uh, One thing we did find out was the next test, instead of just restarting the application code, we actually rebooted Plutos. And that worked. With rebooting the Plutos, we were able to characterize the frequency error under which it could do initial reacquisition. And that frequency error we measured at 2.56 kilohertz, much narrower than the tracking range, which is what you'd expect. That's a little bit disappointingly small compared to the amount of frequency error that the Plutos themselves can generate. Because the Plutos notoriously have a relatively low cost oscillator. It's drifty and its absolute accuracy is not very good to start with. So we've got this existing mystery. We already knew about this mystery, but we didn't learn anything about it yet. Where is the state hiding that gets cleared by a reboot, which is really just a Linux level thing, and yet it prevents the demodulator from working? So more investigation required on that. Um, the next question, all this has been done with external oscillators, locked under GPS discipline oscillator control down to a fraction of a part per billion. We knew exactly what frequency they were both on, and they weren't drifting. Um, so we wanted to go back. I'd rather be able to ship software that works on a stock Pluto with its drifty Cremi oscillator. So we did that. We went back to internal oscillators, starting from where we were with the external oscillators, which was completely with no compensation being added in the Pluto. And we knew that wasn't going to work because we knew that these two Plutos are their native frequency are too far apart to acquire. So in fact, we ran that test anyway, and sure enough, it didn't work. Um, so the next thing we tried to do was run our calibration on the internal oscillators to try to get the internal oscillators to as close as possible to the right frequency uh, on both Plutos. The easiest way to do that I've found so far is to measure the local oscillator leakage from the transmitter. The local oscillator is a nice uh, single frequency. We can dial that frequency up on a spectrum analyzer and adjust it. And there's mechanisms built into the Pluto where you just write to an environment variable and it adjusts the frequency for the frequency error of the clock. So we did that and then immediately ran the test again with reacquisitions, and they worked and they jumped into tracking right away. This is good news. And this is the current test that we're running right now. It's been running for 19 and a half hours so far. Uh, the graphs I'm going to show you here are from about the 18-hour mark. I'm going to try to share that picture. All right, you should be seeing multi-graph. Can somebody confirm that for me?
Yes.
Okay, this is the graph that represents the transmit side. So It's RF loopback. All clocks are the same because it's the same reference oscillator for both transmit and receive within the same Pluto. And let me just run through these individual graphs pretty quickly. At the top, there's this row called bits slash errors, where the black represents the number of bits in this period of time, which is 1 second, and the red represents the number of errors. And you can see for this entire 18 plus hour period, the bit error count was 0 for every second, except the very first data point you can see over there on the left. That's where it's getting set up and acquired. Now, above that, you see several different lines of black and some scattered points. This is a known problem. We talked about this last week. We think this is due to clock domain synchronization, and Matthew is working on a fix for that. You can see the bottom black line is the real one. That one's actually pretty solid. If you zoom in, all the other lines are broken up. They're just individual points. Sometimes it just skips reinitialization because of this clock synchronization problem. The second row is the same graph zoomed in so that you can see that that bottom black line, which is now at the top of the graph, is at about 54,000, which is where it should be, that many bits per second. And the bit error rate is 0. Same thing on the next row, bit error rate is tagged at 0. Now, the next two are the accumulators. They're actually the same graph. Usually it would I have two graphs there, because one could be the entire range of the accumulators as they vary, and the other one could be zoomed in to see the detailed behavior. But because the accumulators are so well behaved in this internal loopback test, RF loopback test, that they don't need to be zoomed in. You can see they're centered around 0. They're not drifting. They're consistent, and the amount of noise is about plus or minus 2,000, and that's fine. That's good work. And that directly results in the NCO adjust, which is the next to the bottom graph, and that shows that the adjust actually being fed into the numerically controlled oscillator has the same behavior. It's centered around 0 and not drifting. The bottom one is just a check on our ability to keep time. You can see that the time is 1.0 seconds per block, plus or minus or mostly plus about 1%, which is good. We now have accurate control over time. So that's all boring. We've had all these results before. This is just a baseline to see that we can still transmit reliably. Now, going to this other graph, this is the receive side. You can see the top graph is very similar. We're measuring over 1 second intervals. And look at the accumulator graph. It has this weird little pattern to it. It starts out a little bit below 0, and then it climbs way up, and it stays there for a while, and then it goes down pretty abruptly. And this is highly correlated with the temperature in the room. This is the temperature in the room during the test, according to an inexpensive little logging interior thermometer. You can see that it was getting hot in the room, got some sun load in the afternoon, plus all the equipment warming up the room. And then as it got on towards sunset, it started to drift down. And then we opened a window, and it plummeted. It was low for a while the window stayed open. Then we closed the window, and it built back up to an equilibrium point around here. It was going to start to climb around as it got warmer in the morning. And this is the same shape as the shape of the accumulators and the shape of the NCO adjusts. These two Plutos are right next to each other on the bench, so they don't get a lot of differential in terms of ambient temperature. There are some differences, though. One of them is a little closer to the spectrum analyzer, which is a warm piece of equipment, and so on. I believe the main difference is that the transmitter is generating a lot of excess heat from the transmit function. So there's a difference, and the difference depends on the ambient temperature, but it's not directly the ambient temperature. So this ran with 0 error rate, except for one little glitch here I see, for over 18 hours. And that's really good news. And the tracking is doing what we expect. The accumulators are moving in accordance with the frequency error. the NCO zoom, the NCO values are, this is uh, the whole range, and this is a zoomed in range. They're behaving themselves. They're staying within a tight range on the short term and then varying to account for the frequency error in the long term. So this is all great. This is as close to working in a realistic over the air environment as we've measured so far. And I'm very pleased with that. We have a couple of mysteries. We've got to solve the clock domain problem with registers, and we have this mystery about the excess state. And there's a bunch of other things we can characterize, and we can improve the characterization on all these things. But this is very nearly a working MSK demodulator. So yay. And that's what we've been up to this week. Probably more of the same next week. We'll try to find some mistakes and fix them.
Wow, thank you so much. I think that's a really nice picture of how it's currently working. So some of the things that we're talking about doing, in terms of the next big stride, are to start incorporating a preamble and some of the required mechanism for incorporating a preamble, which will allow us to synchronize a lot faster and is in our protocol document. Those things are already in the HDL, and what we need to do is to write the application layer code in order to manipulate them, to set them up, and to see if this gives us additional traction. So that's something else that we're trying to get around to try to get to up and running and tested. But I think as Matthew said, this is getting a whole lot closer to a minimum viable product, an MVP, and is a really, really good work. So this is a very, very good results. I mean, we're really happy about it. So if you're interested in this, this is our native digital uplink protocol for our space projects. It's also completely usable and appropriate for terrestrial work. So it's a minimum shift keying open source implementation in VHDL. Our first target is the Pluto SDR because it's so affordable and widespread. Um, the things that we're learning on trying to implement this and get it to fit into the relatively small FPGA on the Pluto will feed directly into any custom hardware that we might design and publish. All right, anything else, Paul, that you can think of?
Um, I'll give it 10 seconds on the remote lab. Um, there are things that need to happen. We're going to need to take some time out at some point, do software updates and some work to hopefully speed things up in the virtual machines. That's still pending. We'll pick a time.
Okay. Yeah, maybe we can make a call coming up here, where things are working really well with Opulent Voice VHDL, and maybe we can get that in. So so thank you. Very appreciated. It's a whole other part of our work is maintaining the lab and making sure the resources are available.
Yeah, for our current purposes, we're for historical reasons, how we got to where we are, the stuff we're running doesn't depend on the the computer in the remote lab. I'm running everything on external machines. Um, so I can continue to do that even if the the host in the remote lab gets into a weird state for a while.
Okay, very good.